Hello and welcome to Lesson 3.3. So in Lesson 3.3 we have kind of a hodgepodge of topics we want to kind of scrounge through to wrap up what we've been doing so far in this chapter. So we've been dealing a lot with radicals. We've been doing a whole bunch with radical expressions and simplifying radicals. What we're going to want to do now is kind of take our simplifying radicals to the next level, and that'll be the meat of the lesson, most of the lesson. But before I go there, I want us to use our radicals to do something useful, kind of an application for our radical skills, for our square roots and cube root skills. And useful the most useful application of dealing with radicals, or using radical skills, is the distance formula. Now, what is the distance formula? Let's actually see if we can think through and build the distance formula. So I may ask you to find the distance between 2 points. Find the distance between, and I could give you 2 points. Like, let's say I ask you to find the distance between the point 2, 4 and the point, let's see, I can't read my own writing. I believe that's 6, 7. 6, 7. Okay. And if I wanted to understand the distance formula, I believe showing a graph would be the best way to understand this. So I have the point 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I have the point 2, 4, which is about right there, and 6, 7, 6, 7, which is about right there. And I'd like to find this distance. Well, getting distances is going to kind of be hard, but we do know a little bit of some background knowledge to help us find this distance. It's easy to find distances straight left and right, and straight up and down. And if I can find this distance up and down, and this distance left and right, then I have the distance of the 2 legs of a right triangle. And I would just be looking for the hypotenuse to find the distance between these 2 points. And remember that you take one side, we'll call it A, and you square it. You take the other side, we call it B, and you square it. And if you add those together, that equals the third side, the hypotenuse, squared. Well, I don't want the hypotenuse squared. I'd like it just to find its length. So to undo the square, I would have to square root both sides. And so to find this distance, all I have to do is square root the other 2 distances squared and added together. Okay, well this is where the distance formula comes from. How do I find the distance from here to here? I just subtract the x values of each point. And how do I find the distance between here and here? I just subtract the y values between each point. Okay? Now I'll go ahead and tell you, order doesn't matter because after we subtract them, we're going to square them and make them positive anyways. So the distance formula, let me actually get it to you written down. The distance formula looks like this. It usually uses a d to represent distance, a big square root, and what we have is x1 minus x2, or you could do it the other way around, x2 minus x1, it does not matter, squared. Add that to y1 minus y2, that's a minus sign that looks sloppy, minus y2 squared. So that is the distance formula, and it comes from the Pythagorean theorem. Okay, so let's find the distance. So remember, each point is xy, xy. They're ordered pairs, they're in alphabetical order. Let's call this point 1, and we'll call this point 2. And it does not matter what order I do this in, but if I want to find this distance, I have the square root of, all right, let's see. Let's subtract our x's. 2 minus 6 squared plus, let's subtract our y's. 4 minus 7 squared. And you could put this in a calculator now, or I think we can probably easily handle this by ourselves, though, with hands. Let's see. 2 minus 6 is negative 4. Negative 4 squared is 16. 4 minus 7 is negative 3. Negative 3 squared is 9. And 16 plus 9 is 25. And the square root of 25 is 5. So I found the distance between my 2 points. Let's do one more really quickly, and I'll do one that's not as perfect as that one. Okay, one more example of the distance formula before I turn you loose. Let's find the distance between the points 0, 3, and 2, 7. Now, if you don't like the negatives, you can always put these first and subtract these pieces. But let's see, distance formula, square root. All right, let's take our x's and subtract them. We can subtract the other direction if it makes you feel better. 2 minus 0 squared plus subtract the y's. 7 minus 3 squared. Okay. Now see, 2 minus 0 is 2, so 2 squared is 4. 7 minus 3 is 4. 4 squared is 16. 4 plus 16 is 20. So I need to find the square root of 20. Now, we worked on some skills last time to be able to simplify this as much as possible. Are there any perfect squares that divide evenly into 20? And your answer is yes. The biggest one would be 4. So I can rewrite 20 as 4 times 5. Remember our product property. I can break this apart into the square root of 4 times the square root of 5, just a bit of review from last time. And then I know the square root of 4 is 2. So if I simplify this down all the way, the distance between those 2 points is 2 square root of 5. Okay, nice. That wasn't too bad, and it reviewed a few skills from last class, like simplifying these radical expressions like that. Okay. Now the next place I'd like to go is, we'd like to be able to do more with our radicals, so we're going to deal with some operations on using the radicals. And so here's what I mean by that. If I simplify something, I can get a number times a radical. That's okay. That's not too bad. But can I add things together? Well, adding radicals is just like adding like terms. So for instance, if I have 3 times the square root of 5 plus 7 times the square root of 5, I can add them because they have the same identical radical part. This would just be like 3x plus 7x. I would say that's 10x, right? So what would I call this? That would be 10, because 3 plus 7 is 10, square root of 5. Now I can only add them together if this part, the radical part, is identical. If it's not identical, then I just can't do anything with it. Let me give you an example of this. Let's say I have 2 times the square root of 3 plus 5 times the square root of 6 minus, I could do adding or subtraction, the square root of 3. Now this confuses people because all these have numbers out front. This one doesn't, but if there's not a number, what's understood to be there is a 1. Okay. Now next thing, which one of these are like? Well, these both have square roots of 3, so I can combine those. So what is 2 minus 1? Well, that would just be 1 square root of 3. Now notice, like when I add the x's, do I change the term part, the x part? No, I just add the coefficients, the numbers out front. Same thing with radicals. We leave the radical alone. So 3 square roots of 5 plus 7 square roots of 5 give me 10 square roots of 5. So I'm going to leave the square root part alone. Now this is not a like term, so I'm just going to bring it over, the 5 square root of 6. And there, I've simplified that as far as I can. Okay, so we can add and subtract them together in that same way. Some other entertaining examples is I may have some work I can do beforehand to make things like radicals. Okay, so let's look at one like this. So let's combine some skills together. So 20 plus 2 times the square root of 45. Let's combine some stuff that we already know with this idea of adding radicals, and we should be able to. Maybe if we can turn these into like radicals, we can add them. Well, are there any perfect squares? Let's simplify both as far as we can get them. Any perfect squares that divide into 20? And your answer should be, yeah. I know that 20, we just did this, is 4 times 5. Are there any perfect squares that divide into 45? And the answer is yeah. 45 is 9 times 5. And so I can break this apart into Square root of 4 is 2. Well, I'll take the time to write it. We're going to break these apart. We'll break these two apart. All right, and now we can handle some of these square roots. What's the square root of 4? It is 2. So I have 2 times the square root of 5. I have a 2 out front. What's the square root of 9? It's 3. And I have a square root of 5. Well, I can do 2 times 3. That's 6. That's not too hard. So I have 2 square root of 5 plus 6 square root of 5. Notice how they weren't like square roots here, and now they're like. I can add them together. So what's 2 plus 6? That's 8. So I have 8 square roots of 5. Okay. So hopefully that's not too horrible. Well, if I can add and subtract radical expressions, can I multiply them? And the answer is yeah, I can. I can multiply and distribute and do all sort of stuff. So consider something like like this. Let's go square root of 3 parenthesis. We'll go with 5 plus the square root of 30. So I'm combining all the skills I have. I know that I can distribute things like this. So I can distribute the square root of 3. So that'd be like 5 square root of 3. Nothing I can really do besides put them beside each other. But here, if I multiply by square root of 3, I have a rule that says if I multiply two radicals, I can smush them under the same radical. So this could be 3 times 30, which is what, 90? Now I'd like to see if I could simplify either of these. Well, that's as far as that's going to go. That's not going to simplify any. But 9 times 10, 9 is a perfect square, isn't it? And so I can begin to simplify this sum. Are any bigger perfect squares fit in there? You don't have your perfect squares here, but for 9, I skipped 9, almost 16, 25, 36, 49. Are there any bigger ones that fit into 90? No. I guess 9 times 10 is the best I can do. All right, well then I can do the square root of 9, which is 3, and I have square root of 10 left in there. Now, are these like radicals? No, they're not, so I can't combine them, so I'm finished right there. Okay, so that I can do that. Now, guess what? If I can distribute, I also can multiply bigger ones like this. Where's my example? 2 square root of 3 minus 7 times 5 square root of 3 plus 1. Like when you FOILed polynomials, I can FOIL these out as well, just in the same way. So 2 square root of 3 times 5 square root of 3. For this being our first time, I'm just going to write them beside each other. Then we can handle the multiplication. Okay. 2 square root of 3 times 1. All right, negative 7 distributed to both, so negative 7 times 5 square root of 3, and negative 7 times 1. All right, so we're going to work hard to kind of make these look nicer. Let's see, so if I'm multiplying two terms together like this, the plain numbers can be multiplied, so 2 times 5 is 10. And I know that I can put the radicals together, 3 times 3 underneath, that'd be 9. Ooh, I can handle that, but let's wait to come back. All right, bring down my plus sign here. 2 square root of 3 times 1 is just 2 square root of 3. Bring down my negative. 7 times 5, I can multiply the plain number. 7 times 5 is 35 square root of 3. And negative 7 times 1, that's just negative 7. Okay, well, a few things to point out here. First off, I can do the square root of 9. That's just 3, so 10 times 3. These are like radicals. I can add them or subtract them. So 2 minus 35 would be what? That would be negative 33 square root of 3. Let's bring down the minus 7. Oh, well now, 10 times 3 is 30. Minus 33 square root of 3 minus 7. And now look here. 30 and minus 7 are like terms. What's 30 minus 7? I can handle that. 30 minus 7 is 23. So I have 23, and I have minus 33 square root of 3. Okay, well that wasn't really that difficult if you take your time with it and do the multiplications. So that's really neat. I can multiply radicals. Okay, there's some things I want you to see here. I had a square root of 3 times a square root of 3. Whenever I do multiply a square root times itself, like a square root of 5 times a square root of 5, that's just going to end up being whatever I was multiplying by itself inside the radical, right? Because that's going to make this a perfect square, and then I can square root the perfect square and get back this 5. This is extremely useful to us because there's one last topic I want to cover, and it's called rationalizing the denominator. Okay, rationalizing the denominator. And here's what this is all about. So if I write you a very simple fraction, like this, we're really picky about what is allowed and what is proper in the bottoms of our fractions. Square roots in the denominator, in the bottom, are not proper. So we would like to be able to fix it. Well, how can I fix it? Well, let's think about this. If I have a square root in the denominator, the only tools I have for changing fractions is to multiply the top and bottom by the same thing. Well, what I just told you is if I multiply the top and bottom by the same thing, I'm not going to change the value. But if I choose something to get rid of the radical, well, one of the few things that would work is multiplying it by itself. Square root of 5 times square root of 5. Now I have to do the top on same and bottom so that my fraction stays equivalent. And so on top I have 2 square root of 5. What happens on the bottom is I have, oh, that's the square root of 25, which I know is just 5. So 2 square root of 5 over 5. So I have rationalized the denominator. I no longer have an radical in the denominator. I got rid of the square root in the bottom. Okay, so it's not proper to have those in the bottom. So I could do this. You get really quick at it because you know that you're going to multiply by the same thing. So if I did something like this, I could even have a square root up top. I don't care about that. But if I have a square root in the bottom, I got to fix it. So I could say, okay, well, what's in the bottom? Square root of 7. Let's multiply the top and the bottom by the square root of 7. Now, that's going to be what? Square root of 14 up top, and on the bottom, square root of 49, which happens to be, you already hopefully know the answer, 7. So I have square root of 14 over 7. So I've rationalized the denominator. Okay, I could even try to be a little trickier. It's not that hard, but go something like 3 over square root of 5x. Well, once again, what's in the denominator? Square root of 5x, and I would multiply by the same thing on top. The top is not going to do much besides just combine those, 3 square root of 5x. But on the bottom, if I multiply the square root of 5x times the square root of 5x, I'm going to get 5x. So that's nice. Now there's only one tricky type. And let me show you that for the last thing. Last thing in this lesson, I might do 2 examples of this. There's only one tricky type. When on the bottom, you have a radical part, like square root of 3, and a non-radical part, like minus 2, added or subtracted to it. Square root of 3 minus 2. Because if I try to multiply, don't copy this, don't do this, but if I try to multiply by the square root of 3 minus 2, that's not going to get rid of the radical part. I would have to FOIL these out, and what I would end up getting is, well, if I took, let me take more time to make sure you understand this. If I did square root of 3 times square root of 3, that'd be square root of 9. And square root of 3 times minus 2 would be minus 2 square root of 3. Negative 2 square root, so minus 2 square root of 3. And then negative 2 would be positive 4. And so what I'm going to end up with is, we're happy this part becomes a positive 3. But this in the middle is what messes us up. That's minus 4 square root of 3 plus 4. And I could add the 3 and the 4 together. 7 minus 4 square root of 3. So I still have a radical in the denominator. So this is where we need something very special. This is where we need something called a conjugate. Okay? Now a conjugate's not that hard to understand. And you'll see why it works because it comes from one of our special products. A conjugate it is if I take this same thing, but instead of doing a subtraction in between, I do the opposite sign in between them. So a plus 2 square root of 3 plus 2. So a conjugate is use the same thing except for the sign. Because this is going to give me a difference of squares, isn't it? You could take the time to FOIL this out. What is it? Square root of 3 minus 2 square root of 3 plus 2. But the middle term, which gave us issues last time, is going to FOIL out, or it's going to cancel out. So square root of 3 gives me square root of 9. Square root of 3 plus 2, or times 2 is positive 2 square root of 3. A negative 2 times that is a negative 2 square root of 3. And negative 2 times positive 2 is a negative 4. Notice that these are perfect opposites, so they will subtract away. And I'll be left with square root of 9 is 3 minus 4. So negative 1. Okay. So you could save yourself time by noticing that this is going to be the pattern of a difference of squares. Okay. And so this will be 3 minus 4. And so on the bottom, I know I'm going to have negative 1. Let me actually just move my scratch work out of the way here. All right. And now on the top here, I'm going to distribute this 5, but I'll have 5 square root of 3 plus 10. Okay. Let's do one more example of these using a conjugate. How about 2 over 3 square root of 2 plus 4. So to get rid of to rationalize the denominator, I'm going to need the conjugate. So I'm going to take the same thing, the 3 square root of 2 and the 4, but instead of using a plus, I'm going to use a minus. And I'm going to need to do the same exact thing on top that I do on the bottom. Okay, so let's do the easy part. Let's distribute the 2. 2 times 3 is 6 square root of 2 minus 2 times 4 is 8. So we got the top. What's the bottom going to be? Now, I'll go ahead and tell you, if you remember the pattern, it's going to be the first term squared minus the second term squared because the middle terms are going to cancel out. But if you didn't, you can take the time to FOIL this out and do all the things. But this is going to end up being 3 square root of 2 times 3 square root of 2 minus 4 times 4. So let's see, 3 square root of 2, 3 times 3. So remember when we multiply these things, 3 times 3 is going to give me 9. And square root of 2 times square root of 2 is going to give me square root of 4. 4 times 4 is 16. Square root of 4 is 2. So 9 times 2 minus 16. And that would be 18 minus 16, which is 2. So we just get a 2 on the bottom. Now, I will say, I didn't do it on the last time, but we should try to reduce this down if possible. 2 divides evenly into both of these. So that'll be 3 square root of 2 minus 4. The 2 can go into both of these. Or if I waited to do it, the 2 would cancel with that 2. But I didn't wait to distribute the 2. Either way, my biggest concern for you right at the moment is just learning to rationalize the denominator here and picking up what this thing called a conjugate is. Okay? But anyways, that's it for today's lesson. Just a few random kind of topics that continue our ability to simplify radical expressions or rational expressions. So we can do operations now. We can use the distance formula to use our radical simplifications, and we can also do operations now with radicals. So we're growing in our ability to deal with these things, and they'll kind of culminate over the next 2 lessons to wrap up this chapter. But anyways, if you have any questions, try the homework and email me, and good luck.